Welcome back to Advent of Code 2021. We're on to day 13. Halfway. Day 13, Transparent Origami. You reach another volcanically active part of the cave. It would be nice if you could do some kind of thermal imaging so you could tell ahead of time which caves are too hot to safely enter. Fortunately, the submarine seems to be equipped with a thermal camera. When you activate it, you are greeted with, "Congratulations on your purchase. To activate this infrared thermal imaging camera system, please enter the code found on page 1 of the manual." Apparently the elves have never used this feature. To your surprise, you manage to find the manual. As you go to open it, page 1 falls out. It's a large sheet of transparent paper. The transparent paper is marked with random dots and includes instructions on how to fold it up. Okay. Oh, it's a... Ooh, interesting. It's a folding problem of some sort. Okay. The first section is a list of dots on the transparent paper. Yeah, 0, 0 is the top left. The first value, yeah, blah, blah, blah. Yeah, okay. Hash is a dot, and dot is an empty, okay. And then there is a list of fold instructions. Each instruction indicates a line on the transparent paper and wants you to fold the paper up or left. So basically the dots merge. Okay, okay. Notice, for example, the 2 dots in the bottom left corner before the transparent paper is folded. After the fold is complete, these dots appear in the top left corner. Yeah, I get it. The transparent paper is pretty big, so for now, focus on just completing the first fold. After the first fold in the example above, 17 dots are visible. Dots that end up overlapping after the fold is completed count as a single dot. How many dots are visible after completing just the first fold instruction on your transparent paper? So... we don't even really need to store the whole grid. You just need to know where the dots are, really. As a hash set, because it's like... when you fold... it's a projection from this grid to a smaller grid. The ones that are in the top half will stay put. The ones that are in the bottom half will go to the top half. So basically you're projecting, which will reduce your dots. Well, no, it won't reduce them. They could stay the same. You could have the same number of dots, just different positions, but it's projecting onto a smaller space. So we don't actually need to store the whole grid here, like all the empty spaces. We just need to know where the dots are. It's literally just a hash set of the dots. How many dots are visible after completing just the first fold instruction on transparent paper? Okay. Seems Seems easy. And part 2, I don't know what could really be complicated. They might ask us to do it 100 times or something. Just do all the folds. If we can do one fold, we can do many. Okay. Alright. So, hello DJ. Doing an origami problem. So we have a bunch of dots on paper, which we need to extract. And then we need to fold the paper along these lines. Yep, I just started, so are you ready? I mean, this seems not too difficult. Folding, so if we've got a bunch of dots on a piece of paper and we fold the paper, basically the dots that, if we're folding the bottom half of the paper up, then the dots that were already in the top half will just stay put. And the dots that are in the bottom half will basically reflect along the folding line. So, wait, if we fold along x equals 655, then what about the dots that are on exactly that line? I think they just stay put as well, don't they? Will they get destroyed? Let me look at the description again. I think we destroy the dots that are on the line. Yeah, because that line just disappears. Interesting. Fine. Maybe they've made it so that there's no dots along the fold lines. Because they didn't give any example of a dot being destroyed. So we just have one big example, one sheet of paper basically. So I guess we want dots. We could just make it a hash set. And wait, why are we making it hash set? Because if two dots exist in the same place, then they are just the same dot. So we're making a hash set to remove duplicates. And for each line, so let's say if comma in line, that means it's a pair. So we just say x, y equals there's also one blank line, so if it starts with fold, then so axis is going to be position 11. And line and the position will be basically the int of whatever's left. So right now, we just want to do one fold. Let's write a fold method. So if you fold a set of dots along an axis, which is going to be a letter X or Y, and position of the axis, I suppose. Then we want to basically create a new set of dots. And then for dot in dots. All right. So the code looks different if it's horizontal or vertical. Can we write it in a way that it doesn't... Yeah, so basically axis, so we're going to say index equals, so the first parameter is the x, and the second parameter is the y, in the way that we've done this. So for dot in dots, if dot index is less than position, that means it's, so if it's horizontal, it's above. If it's vertical, it's to the left. Either way, it stays put. So we put it in new dots. Elif is greater than pos. We have to do the reflection, so it's so it's okay, hang on. How do you do a reflection? So you translate to the line x equals 0, or y equals 0. Then you do negative, because that flips it. And then you translate back. That's how you do a reflection, formulaically. So it's going to be... So the reflected value will be... It's going to be dot index, so minus pos. That just moves everything to the origin. And then we do minus, so it'll actually be pos minus dot index. Then we add pos back. We'll move it back. So it's basically 2 times pos minus dot index. Is that right? Yeah. It's the other way of thinking of it is if you put another line as like the same distance ahead and came backwards, you would end up just over the line. It's easier if I draw it on paper, but I think that's correct. So that is the new index. So we have to say reflected pos equals none. Just make this a list for now. So reflected pos index is going to be 2 times pos minus dot index. Okay, that's reflected. And reflected pos I mean, we could just say equals list dot. It's just a copy of dot, but we changed the reflected axis. And then new dots dot add tuple reflected pos. That's a fold along the axis. I think that's right. So for part 1, we just say the very first time we do a fold, we say we do the fold. If part 1 equals true, just now print the length of dots and don't do that again. So we're going to do all the folds anyway. And if they're on the line, I guess they get destroyed. So that, yeah, that's covered. Got to split on the comma. 607? Is that what they asked for, the number? How many dots are visible? Okay. Correct. Finish folding the transparent paper according to the instructions. The manual says the code is always 8 capital letters. Oh, it's a visual thing. Okay. What code do you use to activate the infrared thermal imaging camera system? Fun. We have to print it out. So then, let's just say, height equals max, dot, add 1 because we want, and get the width. Just say grid equals let's make a grid, and then for dot in dots grid height, no, grid dot 1 dot 0 equals hash. And now for row in grid print. All right, let's see what this looks like. Oh, you have to really squint, but it's CPZLPFZL. CPZLP. Has to be right. Like, I've yet to see an example where he's made it where if you do an obvious wrong thing, you actually get a completely different message, but a completely intact and realistic looking message. That would be hilarious, but I've never seen that happen yet. Like basically swap Z. If you swapped the X and Y axis, well, no, then it would just be mirrored. All right, that was a nice, easy problem. I can see how people would be scared of that problem because it looks like it's using spatial awareness or something, origami. I mean, we've had origami problems which required so much spatial awareness that most people actually had to go. There was one infamous problem which involved moving around on the sides of a cube. And like if you go round the edges of a cube, you appear on certain faces, but you start with a template of the cube, like before it's folded up. So, and you're trying to work out walking around on this template where you would end up on the cube. And I didn't think you really needed to make a physical cube. I did, just for the fun of it, but a lot of people really needed it. So they made a physical cube out of paper, cut it up, folded it up, and then they were able to calculate which edges touch which edges, to work out where you would end up if you're walking around on this cube. So that was cool. A lot of people were posting photos of their cubes. I should have kept mine. I didn't have like glue and stuff to actually wrap it up properly. It was just kind of, I was holding it with my fingers. But yeah, this problem doesn't, it's just a reflection in the axis, so. All right.